Hello and welcome back to AGT STEM. Today we're going to watch a video about uranium. So, without further ado, let's hop to it.
So this is one of our glove boxes. Yeah, so if you just look to the right of the glove box, you'll see that we've got these airlocks, and basically what you do is you put whatever it is you want to take into the box in there, and then you evacuate it, and then you refill it with dry oxygen-free nitrogen. So then you can take compounds which react with air and moisture into the box safely and store them. So this is a bit like what you see pictures of in the nuclear industry when you've got people handling things.
Okay, so next up is uranium, which is my favourite actinide. It's the one I handle in the lab. It's also the boogeyman of the periodic table, I think. As soon as you say uranium to people, people start going, ooh, not sure about that.
This is the boogeyman. This is uranium turnings. You see, they have a sort of dull appearance because when they're cleaned up, they're really very reactive and they react with oxygen extremely quickly. But if you acid treat them with concentrated nitric acid, you get really beautiful gleaming surfaces, but it doesn't hang around very long.
Uranium is the basis of much of nuclear power, and it exists in two isotopes. That's two atoms of different weight. There's uranium-238, which is the most abundant one, and the other uranium-235, which is the one which, when irradiated with neutrons, will split in half and release nuclear energy. And a lot of work has been done, or was done, during the Second World War on the separation of these isotopes of uranium, and including the construction of the biggest mass spectrometers that had ever been made. And fortunately, the separation of the uranium isotopes is really very difficult, which is why it is only very large and rich countries have been able to afford to make nuclear weapons.
This is just oil sat on the top, so just like we had to have oil to protect the potassium, we also need oil to protect the uranium turnings. If you really finely divide uranium turnings, they're pyrophoric, which means they burst into flames in the air, just spontaneously.
But it's actually a really interesting element to deal with. It's got a wide variety of oxidation states. And if you use it in its depleted form, it's actually relatively safe to handle in the laboratory. Now, depleted material only contains a very small quantity of fissile uranium, which is used in bombs and nuclear reactors, about 0.2%. It actually means that the problem with handling depleted uranium is not the radioactivity, although you have to make provision for this. The real problem is that it's highly poisonous, and about half a gram would kill you in a very short period of time because it attacks your liver very effectively.
This is
It's a very short amount of time for something to kill you. So, whatever you do, don't handle, consume, or give other people uranium. Life lesson. Just don't. Don't use uranium at home.
uranium tetrachloride. It's solvent-free. It's a nice free-flowing emerald green powder. And if you dissolve this up in solvents like THF, you get beautiful green solutions from it. And here's another form of uranium. So this is uranyl dichloride, which has got two organic molecules coordinated to it as well. That's this beautiful yellow colour.
So once you've removed the uranium-235, you're still left with a very large amount, more than 99% of the mass of your original uranium is uranium-238, in which you have removed most, but not all, of the uranium-235. And this is so-called depleted uranium, which is some of the densest material you can get. And so it is used where you want something very heavy that's not too large. So, for example, it's used in the counterweights that people put in aeroplanes, in liners, in large aeroplanes, to balance the plane, because you can use it takes up only a small volume of space,
We have to keep it safe and secure in a safe, and we have to fill out huge amounts of paperwork. Many a forest has been chopped down for this paperwork, I'm sure, but it's all very important because you have to be certain that when you're handling your depleted uranium compounds, that you're not going to end up poisoning anybody, and you're not going to end up getting radioactive compounds all over the place. So we have logbooks, and we have to record how much we use and when, and how we dispose of it. We have detectors, which we have to sweep the lab. Well, a lot of people usually start off with, I imagine you glow in the dark, which if I could do that, I'd have passed away a long time before that point. Yeah, it's the boogeyman thing again. A lot of people are quite sort of surprised and, you know, sort of shocked to hear that you're handling this stuff, but actually it's just like most of the chemicals in the periodic table, and once you get past the boogeyman image of it, it's actually a very interesting element to work with.
Most metal or metalloid elements do look like this. It's just that the number of electrons they've got, the number of electrons they can take or they get rid of is what defines their chemistry.
And is that not dangerous? But you know, uranium has this reputation of being so dangerous. Are you not putting us in danger by holding that there?
No, this is depleted uranium, so there's about 0.2% of this is what you would consider fissile. The rest of it is not radioactive. So it's all quite toxic, but you'd have your work cut out to eat this stuff because it's extremely hard.
Well, that was a fun video. I think it's so funny how they call uranium the boogeyman of the periodic table. Also, I apologize for the lighting. It just got so bad because a cloud decided to get rid of the sun. Well, anyway, thank you so much for watching, and I'll see you next time. Stay smart. Bye.